All right, guys. So this is last week. We are going to finish this urinary system in about 2 days or 2 hours. And so let's just get started. So the urinary system basically is a system that we produce our pee, our urination, and this happens in our kidney. So each person has two kidneys. Um, and so you can see that this is a location of the kidney. And basically that a lot of this is just connection from one generate urine, and that liquid, once it's produced, it flows through the urethra and go store it in the bladder and then be out. Uh, and in the kidney, the unit function, the functional unit to process or produce the urination is the nephron. So it's right here. So nephron is the key that generate this urination. Let me see that here, drawing, okay. So here, nephron. So this is nephron. So that's this one here. If we again, so nephron, each kidney has about 800,000 to about 1 billion nephrons in each kidney. And we will learn about that, how nephron produce the urination. And the one thing about the nephron is that it's not regeneratable. So once we have it, we have the limited amount throughout our whole life. And once we use it, if it's injured, it's damaged, they are not going to be regenerated. A lot of our body cells are not regeneratable, although that in the earlier lecture, we learned about mitosis, that cell can reproduce from 1 to 2 to 3 to 4 to 16. But the majority of these functional cells, they are not regeneratable. So just after learning your physiology, one thing you need to keep in mind that you need to take care of your own body, your eating, your lifestyle, doing exercise, regular exercise, all very important, not for anybody else, but for yourself. So you need to treat yourself better by taking care of all your body cells. So let's look at this nephron. So before that, I want to tell you about that. We need to, first thing is that we need to know about that the blood flow goes through this nephron. So here is the nephron. If we made that, if we expand it, this is the expansion of that nephron. So this is nephron. Here is the blood. Blood going in, go through this one here. Here is like a strainer that everything here, the blood has blood pressure, right? A heart pump. So push the blood. This is arterial. So blood going in with high pressure. This pressure is pretty high, about 60 mmHg. So that's very high. So it's very high, it's not drop too much from our large artery. So that 60 mmHg provide large pressure. You can consider that this is the water that you're going to water in your garden with large pressure, and that water coming out will come out from the strainer. So here is the strainer. So here is a strainer. Right here. So everything, basically everything will go through it and go in here. Everything is not exactly true, not cells. So everything means that everything smaller than the monomer. So everything that's larger than monomer will stay in the blood. What is monomer? Can somebody give me some example? What's the polymer?
Glucose would be a monomer.
Oh yeah, good job. Who is that?
Oxygen would be a polymer.
Who is that?
Eddie.
Eddie, good job. Thank you so much. Yeah, monomer. Come on. You want to get extra points? Just, you know, provide your answers.
Amino acids.
Yeah, amino acid.
Like lysine.
So everything like, for example, glucose compares to the polysaccharide, amino acid versus protein. So protein is polymer. This is polymer. This is monomer. So in the blood, this monomer will go through, but not protein. What's the major protein in the blood?
Albumin.
Albumin, good job. Albumin,
Yeah.
the major protein in the blood, but it's not going through. So everything like larger than monomer, only the monomer. So here is everything smaller, including the monomer, will be here. So here we will see glucose, we will see amino acid right here, and the water and the ion. So basically go through here, we have the monomer, we have water, we have the ions go through here, and the protein coming here, flowing out. For example, protein is the, and also cells is not going through, like red blood cell, white blood cell is not going through. So when we measure, one way to detect our glomerular infection is to measure if we have protein here. If you see the protein in your urination, it means that your strainer is too wide, is too open. And that will indicate that here you have some infection. Normal healthy people, we should not see any protein in our urine, or very little. No cells, no protein, it's only monomer. We may see monomer, we may see glucose for a patient with diabetes. Water for sure, ion like sodium, potassium. Okay, so that's that. So that's the blood, and in this portion is called tubule. So let's, before we go in there, let's look at the blood. So here is the blood system that's going into, here is called, this portion, this like strainer is called glomerular capsule. So glomerulus right here. And so basically blood coming in here, arterial, and flowing out. And then here is the strainer. So basically here is the capillary, water going, everything going here, and start to flow. And because once this strainer is basically only limited size, but a lot of good stuff pass through. For example, glucose. Glucose is important fuel. We don't want to lose any glucose. Amino acid, we don't want to lose any amino acid. So glucose, amino acid will then coming back into our body, into our blood, and then we can use it. So here we have this portion is called filtration. This A is called filtration. Right here, A is called filtration. Everything fills through. Filtration is driven by pressure. So here we have high pressure, push everything through. And then we have B is called reabsorption. This reabsorption is selective because we don't want to select, we don't want to reabsorb anything like toxic stuff. Everything like our medicine that we eat, our liver metabolize it. Remaining portion is toxic that we want to, basically those are small molecule. Our body really don't need to anything, don't really need to do anything. We just let it go through the kidney and it got filtered and it got filtered out. This reabsorption is very selective. Basically, it only reabsorbs something that's good for our body. So our body knows that glucose is important, so we selectively receive those back to our body. Amino acids are important. Some ion, if our body is lack of ion, like calcium, we will reabsorb it here. Sorry about that. All right, we will reabsorb it here. But other than that, we basically just leave everything in here and we pee out. So here is reabsorption. Here we also have a process called secretion. Secretion is something that's too much. It's filtered, but this filtration is not 100%. So still some fluid goes through here. And this secretion, the major secretion has two. One is acid. That if our body is too acidic, our kidney regulate it by secrete hydrogen. And potassium. This potassium secretion is controlled by aldosterone. We will learn about it, aldosterone. So that's secretion. So here we have the filtration, reabsorption, and the secretion. And then the blood coming back, C and B, sorry, same thing, secretion, reabsorption, and the blood coming back into our body, go back to our heart. So before we talk about this, so basically we will learn how these 2 days, we will learn basically all these things. We will learn filtration, we will learn about reabsorption, we will learn about secretion. That's it, only these 3 things. But before we look into that process, these 3 processes, we need to know their structure. And the structure has 2 portions. One is blood vessel, and the other one is the nephron. In the blood vessel, we have, so we will learn first thing is the structure. So it's very much like anatomy. Structure we need to learn first is the blood vessel structure, and then we will learn about the tubule structure. So that structure. And the second thing, once we know that, then we will learn these 3 processes, these 3 functions. Filtration, reabsorption, and the secretion. So that's 2 major things that we will learn. So let's start first thing first, structure. Blood vessel structure. This is very important. It's like when we learn about the cardiovascular system, we need to know the structure, the anatomy first. We need to know that the blood coming from the vein into the right atrium, right ventricle, etc. So that is the structure. Here we will learn about the same thing, the structure, the blood vessel. So the blood vessel is that here is the artery. Here going in, we have the afferent arterial. Let's use the other one here. Here, let's use this one here. So the renal blood flow. So this sequence is very important. You will see this one if you want to do good with your final exam. Remember this procedure, remember this sequence. All right, so you have the afferent arterial, so that's coming in. And the following that is the capillary. This capillary is called glomerular capillary. And then you have the efferent arteriole. And then you have the peritubule, this tubule, so that's peritubule capillary. And following that, you go into the vein, it's a renal vein. If we look at this picture, like less cartoonish picture, we have this afferent is coming in, afferent arteriole, glomerular capillary, efferent arteriole. Then it goes through the peritubule, just right next to the tubule, peritubule capillary, and then renal vein. So that is the sequence of the blood. Any questions? So that's the structure of the vessel. So we finish this one here. Blood vessel structure. Any questions? In here, in this blood vessel structure, we basically cover all the blood vessels that we mentioned before. We cover artery, we cover the capillary, we cover the veins. So here we have all the three. In arterial, capillary, and the vein, in which portion we have substance exchange? Arterial, capillary, or vein?
Capillary.
Capillary, Lulu! Thank you so much, Lulu. Capillary. So here we have two capillary bed, glomerular and the peritubule. So one thing you need to know that in that capillary, substance exchange, there is a procedure to call that exchange. In the glomerular capillary, this substance exchange is to produce filtration. So everything filtered through, every small substance filtered through filtration. In the peritubule capillary, we have the reabsorption and the secretion, these two processes. So that's the, and then we have everything else that's going to be P out. This P out has a term, it's called excretion. So here is called excretion. Excretion equal to filtration, that's filtered right here, minus reabsorption, we got it back to our body, plus secretion. So that's excretion. This filtration is, among all this, filtration is the most important one. The major, that's why we make, to detect the kidney function, we detect the protein, because protein define how well our filtration function is. This filtration is also called glomerular filtration. Filtration. The rate to go through it is called glomerular filtration rate. It's also short for GFR. So this GFR is one of the major functional quantity to quantify, to define our kidney function, glomerular filtration rate, GFR. And this is also that, do you guys remember this GFR, these three letters represent something that we just learned last week?
Glucocorticoid?
Yes, yes.
It's the three layers of the adrenal cortex.
That's
Yeah.
right. That's why that's this GFR. When people think about GFR, the direct link, direct meaning of that is glomerular filtration rate, and that is very important. So and the filtration, reabsorption, secretion overall is called excretion. So that's what's gonna be excreted out. So that's the structure of the blood vessel. Now, next one is the structure of the tubule. Structure of tubule has this several portions. First is the glomerulus, right here, glomerulus. And following that, this is called the proximal. This portion is called proximal convoluted tubule. And then we have this U shape. This U shape is called loop of Henle. This is the loop of Henle. Loop of Henle, we have the descending and ascending, coming out and coming back. And then we have the proximal, then we have the distal convoluted tubule. And following that, we have the collecting tubule, and the collecting ducts. Collecting tubule means that here we start to collect urination. This is one nephron, here is another nephron. Every nephron will join together with this collecting tubule and the collecting ducts. Collecting tubule and collecting ducts may located in, so this is the kidney. Kidney also has this portion, is called the cortex region. This is called the medulla, and so here is the cortex. So this outer portion is called the cortex. This inner portion is called medulla. So this collecting tubule is cortical collecting tubule and the medullary collecting ducts. So that's the structure of the tubule. So before we jump into the function, we need to know the structure. And the structure includes the blood vessel structure and the tubule structure. In the blood vessel structure, we have the afferent arteriole, glomerular tubular, glomerular capillary, efferent arteriole, and then peritubule, then the vein. As for the nephron, the tubule structure, in the beginning, we have this glomerular capsule, and then we have the proximal, loop of Henle, distal, collecting tubule, collecting ducts. Any questions? All right. So that's basically this whole region. Let's kind of give it a quick review about what they are. First, we have this portion. This glomerulus is also part, if we is also encapsulated by this capsule. This is called the Bowman's capsule. Basically, their function is like a strainer. Everything small enough will get through. And then here in the proximal, overall this tubule, although it seems to be very complicated, we make a turn here, turn there, a lot of turns, even though it's very complicated. But I want to give you like a concept. You need to have that concept first. Basically, you have the near and the distal and something between. In the near portion, this is called proximal. The concept is that the proximal do the most job. Almost everything need to be reabsorbed is in the proximal. Everything good is in the proximal. So basically the remaining part is the small modulation of what's in the remaining. In the beginning, in the early segments, this proximal have done all the job. Our body need, when we secrete monomer, glucose, amino acid, water, ion, which one is the most important to our body? Glucose, amino acid, water, ions.
Water.
Water is important. Very good. And what's the second one?
Glucose
Glucose.
for energy, yeah.
Energy. And what's the next one?
Probably the ions.
Ion,
I think.
Ion, we have a lot. We have more. Amino acids is very important because that's our building block of our protein and our body function.
Oh, yeah, that's true.
Yeah. So here, glucose, you need to work. You need to gather. You need to spend money to buy it. Protein, you also need to spend money to buy it. So these two are very important, and we see them in our urination. We don't like it. We want to take it back because you work hard, you get paid, and you spend money on the food. Basically glucose, amino acids, you have to pay for it. And you see it in urination, you want to take it back. 100% of this glucose and amino acids are reabsorbed here in the proximal tubule, 100%. So remaining, they don't do that work. Just in the beginning, the essential part is taken back to our body. Water is very important. Ion, the major ion that we take it back is sodium. So here we reabsorb sodium about 65%. And by doing so, we also reabsorb water 65%. Because that is water reabsorption is following the osmotic pressure. So when we reabsorb salt, that will drag the water with it because of the osmotic pressure. So here, in the beginning, we absorb everything we needed. The remaining is just a little like modulation. So you can see that, if you can see that here, we reabsorb glucose, amino acid, water, and the salt. The major thing are all reabsorbed in the proximal. So that's a concept you need to have. And everything important in the proximal. What's the remaining is actually water. So that's a concept, but we will see through. We will get to the detail about it. But the concept here is you need to have is that filtration, filter everything small. Reabsorption in the proximal do the major work. Glucose, amino acids, 100% reabsorption. Then water, salt, 65%. And we have everything remaining here, but in the remaining portion, the major work is the water. And here we need ADH. Earlier we learned about it, ADH, to reabsorb this water, because water is also very important. Otherwise, water will be pee out. So that's that. Any questions? All right. So first one is the filtration. This filtration is called glomerular filtration. So here we have the blood going in. This is the afferent. This is the efferent. So blood going in, and the pressure is very high. The pressure is about 60 mmHg. So the pressure is very high. Everything is pushing out. Not everything, small things. So, and this also encapsulated by Bowman's capsule. So here is called Bowman's capsule. So number here is that this one filtered 180 liters a day. Our blood fluid portion 3 liters for our body. So our fluid goes through this process 60 times a day. So that's how we keep our blood clean. Everything toxic, not just toxic, everything metabolic waste products will be filtered through, will go through this one here. And by doing so, we have the risk because everything's small, including glucose and amino acid. So we have the risk to lose those. So this nephron, this filtration doesn't care. They just filter everything through. And the job of this nephron is to keep the important thing back. So that's the filtration. This filtration comes into one very important measure is called GFR, glomerular filtration rate. This filtration rate controlled by two factors. One is filtration. So filtration is controlled by the pressure. Raise hand, Lulu, what's that?
In the previous picture, wouldn't aren't they switch? Efferent and efferent?
Yeah.
Wouldn't the efferent be afferent compared to our other pictures?
Efferent is coming in. Efferent, E means exit.
Okay.
Means going out. So it's efferent coming in. This is glomerular capillary and efferent coming out.
Okay.
Yeah, thank you. Any other questions? All right. So this filtration has two factors. One is pressure. This pressure, so filtration pressure. Pressure basically is defined by the blood pressure because this is coming from the efferent arterial, and that 60 mmHg basically is very much controlled by our heart pressure, our blood pressure. And the next one is also controlled by how much it got filtered is by the strainer. So this is the constant factor here. The strainer. If the strainer is very wide, everything filtered through. If it's small, then even though the pressure is high, the amount to get filtered through is small. And this KF also defines that what the strainer also defines that what can be filtered through. Usually, if it's healthy nephron, only the monomers smaller than the monomer will get filtered through, but not the polymer. So that's GFR is very important. That is a function to define these glomerular filtration. And then the next step is the proximal convoluted tubule. And as we key here is that it reabsorbs 100% glucose and amino acid within the renal capacity, meaning that for like the general body function, you should not see any glucose, amino acids in the urine. But for patients whose blood has too much of the glucose, then here the reabsorption may reach to the maxima that it cannot reabsorb furthermore. And then you probably will see some glucose. For example, diabetes patient, you will see glucose remaining. That's because that it's already reached the maximum capacity of the reabsorption located in the proximal convoluted tubule. So even though we don't have the real exam on this one, but you must know what you must know is that when people ask you glucose reabsorption, amino acid reabsorption, where is it? You must answer the proximal convoluted tubule. You will be given the option like proximal convoluted tubule, loop of Henle, ascending, descending, ascending, distal convoluted tubule, collecting tubule, collecting ducts. Please don't answer. Please don't choose on the other one. Just choose the proximal. Proximal is the very beginning of the nephron, And all these essential substances are reabsorbed in the proximal convoluted tubule. Please. Can you do that? Yes, thank you. All right, so this proximal convoluted tubule reabsorbs 100% glucose and amino acids. Those are essential. That basically something we pay for. So we want to reabsorb them back to our body. And the other things are salt, 65%. So if you eat more, you reabsorb more. If you eat less, you reabsorb less. It will be 65%, very constant. And that will draw water back to our body due to the osmotic pressure. And then we also reabsorb 85% of bicarbonate, HCO3 minus. This is bicarbonate. We probably didn't really think about it. This is also considered an usable substance in our body. It's because that our body need to have a buffer system. And the major buffer system in our blood is the bicarbonate. So we need it in our blood as a way to serve as a buffer system to maintain our body's acidic level. So bicarbonate will be absorbed as well. This tubule just give you a example that we will see this tubule throughout the entire nephron. This tubule, like this one here, is constructed by the epithelium cell. Epithelium cell is called tubular epithelium. Each of these cells has two phases. One phase, the luminal or the urine side. The other phase, the body, so interstitial. This is the body. Basically here is reaching into the blood. Capsule, capillary. So it has one phase to the tubule luminal and the other phase to the blood. The phase to the luminal is called the luminal side or apical side. The phase to the interstitial is the basolateral side. So this is the basolateral side. So here is a cell. Each cell cells nucleus, luminal side, basolateral side. And all the cells also has this sodium potassium pump. These pumps are all located in the basolateral side because we don't want to regulate everything with that urine here. This is more like selective selection to conduct the reabsorption or the secretion. But for the sodium potassium ATPase, they are all located in this side. So we have the potassium pump in and the sodium pump out. So that's the luminal like cells. Any questions? And so here is the glucose reabsorption. This is the glomerular glucose coming in. It's reabsorbed in the proximal. So this is loop of Henle. This is loop of Henle. Supposedly this is still in the proximal. So don't get confused. This is still in the proximal. So these are we have two major glucose transporter, sodium glucose transporter, because it's co-transport with sodium, SGLUT. 1 and 2 are all located in the proximal convoluted tubule. You don't need to worry about that 1 and 2 thing. You just need to remember that everything, now 100% is in the proximal, glucose reabsorption in the proximal. Glucose reabsorption. So in the proximal. SGLUT are sodium glucose co-transporter, SGL glucose T. 1 and 2 are in the proximal, and 90% are by SGLUT2, 10% by SGLUT1, and basically that everything is in the proximal. And they basically is co-transport with the sodium. So you must remember is that glucose is reabsorbed in the proximal convoluted tubule. If you do need to remember extra more, show you're standing out. You can remember the SGLT2 and 1. And by doing so, you also memorize that this glucose transporter is a sodium co-transporter. So it's right here, sodium co-transporter. That makes this transporter effortless. It's because that here in the basolateral side, we have this sodium potassium ATPase. It pumps the potassium in, sodium out. By pumping the sodium out, provide this low sodium in the cell. And that provide this gradient concentration for sodium to go in. So when sodium going in, it activates this transporter, will bring the glucose going in as well. And then glucose diffuse into our body. Same thing applied to the amino acid. Amino acid is also a sodium co-transporter. So in the proximal, glucose and amino acids, 100% reabsorbed. And their reabsorption are all sodium co-transporter. Any questions? All right. And that transport has maximal. It means that if we reach that maximal level, we will see glucose in the urine. It's called glucosuria. That is glucose in the urine, and it's commonly seen in patients with diabetes. That's because our plasma has hyperglycemia. That has too much of the glucose in the blood. And amino acid is also reabsorbed by.
Can you please enlarge the screen, please?
Say again?
Can you enlarge the screen? It's so small.
Oh, really? Let me do this one here. Let me do this one. How about this one? Is it good? All right. Yeah. And then the amino acid is also reabsorbed 100% into our body through this sodium co-transporter. And in the proximal convoluted tubule, we also reabsorbed bicarbonate. That is that this bicarbonate is an important buffer system. If our body is too acidic, it will move into this direction. If it's less acidic, it will move into this direction. So this bicarbonate is an important, right? It's an important buffer system. And about 85% of the bicarbonate is reabsorbed in the proximal convoluted tubule. And this is the reabsorption process in the urine. This is the interstitial in our body. In the urine, we have this bicarbonate. It will be reabsorbed into our body. So this process is complicated, but I just want you to remember one thing, just one thing, that the reabsorption of each bicarbonate let me just, because I need to draw it, I will just do this here. So here, when our body reabsorbed each bicarbonate, each one from urine into our body, we secrete one hydrogen. Hydrogen is secreted. Hydrogen is right, where is this? Are there? Hydrogen, anyway. So hydrogen right here. So in our body, in the cell, hydrogen is it peeing out. Pee out. And bicarbonate reabsorption. So the only thing you need to remember is that whenever our body reabsorbs and bicarbonate, we secrete hydrogen. I probably see here, we removed one hydrogen as an exchange. So that's the only thing you need to remember. Okay? Any questions? All right, then. Go back here. So bicarbonate is, okay. Our body has several mechanisms to regulate our body's acidic level. And the major three mechanisms are buffer system. Our plasma has this buffer system, bicarbonate. Our organs also participate in the acidic level regulation. Two major organs are kidney, as we mentioned before. By reabsorption, bicarbonate, we secrete kidney. And we secrete hydrogen. So that way we can reduce our body's acidic level. So kidney is one organ to regulate our body's acidic level. Another organ is the lung, respiratory system, because that removes CO2, and that way we reduce the bicarbonate. So our body has two organs to process the acidic level, to regulate our body's acidic level. One is in the lung, the other one is in the kidney. In the lung, it reduces CO2, and that way it reduces the bicarbonate, because CO2 transportation is to be converted into the bicarbonate. In the kidney, it reduces the hydrogen directly. And because of these two organs are important in regulating our body's acidic level, when our body develops the acidic disease, for example, if our body has acidosis or alkalosis, we can classify it into either the metabolic acidosis, alkalosis, or respiratory acidosis or acidosis. So just by measuring the blood acidic level, we defined whether that is acidic or alkalotic. Following that, we need to know that which is the cause, whether that is the kidney's problem or is the lung issue. Then we can classify further into the metabolic or respiratory cause. And that lead to this is very important. This is the summary. This is, after all, we already learned that lung has the function to regulate the acidic level. Kidney also has the function to regulate the acidic level. And so we have this metabolic acidosis, metabolic alkalosis, respiratory acidosis, or respiratory alkalosis. And how do we define which one is which? So first of all, we measure the pH in the blood. So for the acidosis, pH is low. But to distinguish whether that is metabolic or respiratory, we measure the either the PaCO2. If the PaCO2 is not normal, then we know that is respiratory because lung control our PaCO2 means that arterial CO2 level, and the CO2 is regulated by the lung. If we may, but we should see bicarbonate is normal. If we see the bicarbonate vary, that will mean that this acidic or alkalosis is caused by the kidney, and that abnormality can be diagnosed as a metabolic acidosis or metabolic alkalosis. So that's 3 quantity we can measure in the blood: pH level, PaCO2, and bicarbonate. And by measuring this, we can classify it into respiratory versus the metabolic acidosis or alkalosis. Any questions? All right. So then the next one is loop of Henle. This loop of Henle has this 2 segments. One is the descending, is leaving away, and ascending. So in the descending, the major work is to reabsorb about 20% of the water, and the ascending reabsorb is impermeable to water, but it reabsorbs salt, 25% of the salt, and 10% of bicarbonate. So after all this one here, bicarbonate, it's almost like 90% reabsorbed. Before we have 85% here, plus 10% is 95%. So bicarbonate is very much get back to our body. And the water and the salt. Water permeable up to here, up to this point. Remaining is impermeable. So water, if water need to be absorbed, it's only up to here. Remaining basically is not. Tubule won't reabsorb water furthermore, unless we have ADH. So here is loop of Henle. This is the glomerular capillary, Bowman's capsule, filtration, and then proximal. We have the proximal reabsorb everything, every major thing, glucose, amino acid. Then we have the loop of Henle, descending, ascending, come back to here. Then here is a portion called macula densa. So right here, this is the macula densa. Macula densa, so here we go away from the blood glomerular, and then here come back to reach it here, glomerular here. So here is an important region to regulate our, to produce the renal system. That's right here. So earlier we talked about that. This is called the tubular glomerular feedback, that it detects what is going on in the blood. So if this filtration, if this blood flow is low, it means that we lose a lot of fluid. Then it will trigger the release of renal. Or this region detects our sympathetic activity. It will also trigger the release of renal. So that's a region that's kind of like a urine system sending signal to regulate our cardiovascular system.
More like a thermostat. for the urinary system.
Second, sorry.
It's more like a thermostat.
Okay.
Yeah, when it's low or it's high, it activates or it doesn't.
That's right. That's right. That's right. Yes. Yeah. So if the urine is low, it means that a lot. So say the filtration is low. If the filtration is low, then fluid is low. Then the fluid is low, then here it will know because it already goes through this one here, coming back here. So if the filtration is low, the fluid, urine has low or fluid is low, then it will trigger it here. It will know that our body has too low, the blood pressure is too low. If the pressure is too low, filtration is low, then the fluid flow is low, in the urine is low. And so that will send back signal here, not directly to here, because it need to control our heart, it need to control our blood pressure to boost it back to the higher level. And that pressure will then provide the filtration pressure needed. And that will bring back the urination. So how do we do that? Here is the macula densa. This is transection of this one here. So this is the tubule transection. Here is the macula densa. So this is transection here. This macula densa tubule located right next to the afferent arteriole and efferent arteriole. So if it detects the low flow, when the flow is low, it usually detects the low sodium. So here, basically detect low sodium here. If the flow is low, everything is low, and the sodium will be low. And then it will tell these cells in the arteriole and the efferent arteriole to produce. This cell is called juxtaglomerular cells. Tell this cell to release renin. So key here is that this is macula densa. The major function of the macula densa is to provide like thermometer, like Simon mentioned about, and then it will cause the juxtaglomerular cells to release renin. And then you know the rest, because here is the renin-angiotensin 2 pathway. So kidney, we have this graph go over so many times. Renin, so the kidney, either the low sympathetic activity, low pressure, or low sodium delivered in the distal tubule measured by the macula densa. It will trigger the kidney to release renin. And the cell to release renin are the juxtaglomerular cells to release renin. And then you know the rest. Renin will then convert angiotensinogen to angiotensin 1. Angiotensin 1 then convert to angiotensin 2 through ACE, angiotensin conversion enzyme. And then angiotensin 2 cause the vasoconstriction. This one will increase TPR. Right down here. So this one will increase. Okay, right here. So this one will increase TPR, total peripheral resistance, vasoconstriction, and the angiotensin 2 also will cause our body, our adrenal cortex to produce aldosterone, and to our brain, hypothalamus, to the posterior pituitary gland to release ADH. ADH will cause our body to reabsorb water, so it will cause water retention. This water retention fluid in our body will provide the venous return, and that will provide the fluid back to or hard venous return. Higher venous return will cause higher stroke volume. Stroke volume increase will cause the cardiac output increase. And so here we have CO increase. TPR, we learned that BP equal CO times TPR. So the end, we have CO increase, TPR increase, we have the BP increase. When we have the blood pressure increase, we will have here in the very beginning here, we have the blood pressure increase. A lot of blood pressure will push the fluid into the tubule, and that will increase the filtration rate. GFR will increase. BP increase will push the fluid go through, cause the filtration increase. And then it will kind of adjust the fluid back to normal. Any questions? So just a quick summary. I will just end it here because we should be able to finish everything Thursday. We only have about less than half of it. So just a quick summary of what we have learned today. We basically go through the structure of the nephron. The structure includes the blood vessel structure. So here is the blood vessel structure. From the afferent to the glomerular capillary to the efferent, peritubular capillary, then the vein. Blood vessel structure. And then we also go through the tubular structure. Tubular structure from the proximal convoluted tubule to the loop of Henle, and then distal, then collecting tubule, collecting duct. So we learned that the structure of this nephron. Then we go through, this is very much like hiking. We have a hike from the beginning, filtration, proximal, and the loop of Henle. We have not finished the whole trail yet, but we actually, it's already almost like more than halfway through. But even though that we are not finished yet, but you already learned the major portion. That is the glucose reabsorption, amino acid reabsorption. Those all happens in the proximal convoluted tubule. Any questions? All right, guys.